What if the most effective water purification method on the planet, in the year 900 CE, fit in one hand, cost nothing to produce, and required no filter, no cartridge, no service schedule, and no monthly charge? What if the global industry currently billing you for the same outcome generates over $35 billion every year? Documented in Grandview Research's 2022 market analysis of the global water treatment chemicals sector. Precisely because almost nobody connects the copper fittings on a Norse longship to the water container sitting on their kitchen counter right now. Not almost solved it completely. The physical evidence is in the copper ladles, copper vessels, and copper-lined storage containers recovered from the Burka trading post excavations in Sweden. Documented by archaeologist Birgitta Ambrosiani in Burka Studies, Volume 1, published by the Swedish History Museum in Stockholm in 1992, Copper Touching Water. On every long-distance Norse vessel. For 3 centuries, without interruption. It costs $1 to replicate today. It worked then, it works now. There is one specific property of copper that Norse crews understood, and that the water treatment industry spent the better part of the 20th century routing around. What that property is, and exactly why it works, is coming up in less than a minute. Viking crews did not get to test their solutions in comfortable conditions. Every technique they used was stress-tested by open ocean, starvation, and temperatures that could kill an unprotected person before the sun moved one hand width across the sky, for months at a time, with no resupply possible. If the water went bad, the crew died. Not struggled. Died. The copper artifacts that prove what those crews understood are still physically present today, in the fittings and vessels pulled from the Burka trading post, in the copper rivets and hardware recovered from the Skudelev ship excavations at the Viking Ship Museum in Roskilde. Documented by Ole Crumlin Pedersen in Ships and Boats of the North, Volume 4, published in 2002. In the bronze and copper fittings from the Gokstad ship, first excavated by Nikolai Nikolaisen in 1882, and held at the Viking Ship Museum in Oslo. These objects did not survive because someone carefully preserved them. They survived because the metal itself resists what water carries. The physics does not expire. The reason you're paying for the same outcome every month is not because the modern solution works better. A copper fitting cannot be invoiced. But here's the part the industry hoped you would never think to ask. Exactly how copper kills what it kills and why Norse craftsmen built that knowledge into the structure of every ship they sent across open water. That mechanism is what comes next. This is not a new idea. The antimicrobial property of copper was formally recorded in the Western scientific record by Swiss botanist Carl Wilhelm von Nägeli in 1893. He named it the oligodynamic effect, which just means that metal, in amounts too small to see, poisons the outer wall of a bacterial cell on contact. Von Nägeli demonstrated this by placing copper in water and observing that microbial growth stopped. Not slowed, stopped. His findings were published in Über oligodynamische Erscheinungen in lebenden Zellen, Zurich, 1893, and are still cited in modern microbiology textbooks. Von Nägeli called it a discovery. Norse shipbuilders had been practicing it for 300 years before he was born. The Archaeological Museum of the University of Oslo holds copper and bronze vessels from Norse domestic contexts dating to the 8th and 9th centuries CE, recovered from settlement sites documented by archaeologist Bergljot Solberg in her analysis of Norse material culture published in Norsk Arkeologisk Tidsskrift in 1985. Copper was not decorative on those ships and in those settlements. It was chosen for containers that touched food and water, specifically because Norse craftsmen had observed across generations that water stored in copper stayed clean longer than water stored in wood or iron. Not as a theory, as a practical observation that kept whole crews alive on crossings where the nearest drinkable water source was weeks away. That observation became commercial inconvenience in 1914 when the first large-scale municipal chlorination systems were installed across American cities, a process documented in historian Michael McGuire's History of U.S. Water Treatment, The Chlorine Revolution, published by the American Waterworks Association in 2013. Chlorination worked. Nobody disputes that. But chlorination also required infrastructure, licensed engineers, chemical suppliers, and ongoing service contracts. A copper vessel sitting on a shelf required none of those things. You cannot sell a subscription to a copper bucket. You can sell one to a chemical treatment system every single month. That is the complete explanation. Nothing was banned, nothing was hidden. The billing cycle simply did not have room for free. What Norse trading communities had refined across 3 centuries, built into the physical design of their ships and settlement water systems, preserved in the copper artifacts now held at the Swedish History Museum and the Archaeological Museum of Oslo, became worth less than a replacement filter cartridge you throw away every 90 days. That is not a complaint. That is just math. At its height, the Norse trading network connected Newfoundland to Constantinople to Baghdad, documented in the eyewitness account of Arab traveler Ibn Fadlan, who observed the Rus Vikings on the Volga River in 921 CE. His account, preserved in manuscript at the Meshed Shrine Library in Iran and translated by historian Richard Fry in 2005, describes in direct detail the river vessels, the trade goods, and the daily practices of Norse crews operating thousands of kilometers from any familiar shoreline. Every single crew operating across that network solved the water problem without paying anyone, without a filter, without a cartridge, without a service contract. The Beverage Marketing Corporation, in their 2019 annual report on U.S. bottled water consumption, documented that American households spend over $400 per year on bottled water alone, not counting filter units, replacement cartridges, or installation fees. Norse crews running those same long-distance trade routes paid nothing. The physics they used has not changed by a single variable since 900 CE. It is in your kitchen right now, and almost nobody is using it. If that number stopped you, this channel is here for exactly that reason. Every week we recover one technique the modern market assumed you would never find. Subscribe and hit the bell so you do not miss the next one. You have seen this your whole life and just never connected the dots. A copper penny left in a vase of water keeps cut flowers alive longer. Gardeners have known this for generations without knowing why. Old farmhouse families in Scandinavia stored drinking water in copper pots, a practice documented by ethnologist Niels Lithberg in his 1914 survey of traditional Nordic household implements, published by the Nordiska Museet in Stockholm. Researchers at the University of Southampton published a study in Applied and Environmental Microbiology in 2006 showing that copper surfaces in a clinical setting eliminated over 99% of bacteria that survived on steel surfaces and did so within 2 hours of contact without any added chemical. Not reduced the bacteria, eliminated. The mechanism is not complicated. Copper releases ions into the water around it. An ion is just a particle smaller than anything you can see, the size of a single atom. Those ions travel through the water and attach to the outer wall of a bacterial cell the way a splinter catches on cloth, and they tear it open. The bacterium cannot adapt to this. It cannot build resistance the way it builds resistance to antibiotics. The copper does not run out of ions. It keeps releasing them as long as it sits in water. Think of it this way. A spoonful of bleach in a bucket of water kills what is in that bucket right now. You fill the bucket again tomorrow, you need more bleach. Copper is different. Put a piece of copper in that same bucket, and every time the water is refilled, the copper is still working. It does not get used up. It does not expire. It does not need a replacement. Most people who try this make one mistake at the very first step. It is not the copper they choose. It is not the water they use. It is one specific part of the preparation. And it is the difference between water that is genuinely safe in 6 hours and water that still carries exactly what it carried when you poured it in. Here's what you need. I want to be honest with you about every number. 1 piece of solid copper. Not copper-plated, not brass, solid copper. A short length of copper pipe, the kind sold in every hardware store for residential plumbing, costs about $1 for a small piece. The piece you need is roughly as long as 2 of your fingers placed side by side and about as wide as your thumb. A copper coin works too, with one important condition. Pre-1982 U.S. pennies are solid copper, documented by the U.S. Mint. Post-1982 U.S. pennies are zinc with a thin copper coating and will not work. The ions come from solid copper, not from a coating that is a few atoms thick. A solid copper plumbing cap, or end fitting from the hardware store, is the most reliable choice and the easiest to confirm. 1 container, glass, ceramic, or food-safe plastic, something that holds roughly as much as a large cooking pot. A 1-gallon glass jar works perfectly. That is genuinely it. Here's the one thing most people get wrong when they try this. They drop the copper in and drink the water an hour later. Norse crews who struggled with waterborne illness, and some did, documented in the ship burial records, recovered from Hedeby during Herbert Yankun's excavations between 1930 and 1939. Published in Hythabu, Ein Handelsplatz der Wikingerzeit in 1956, were not using the wrong metal. They were not using contaminated copper. They were pulling the water too early. The copper needs time. The ions need time to disperse through the full volume of water and reach every part of the container, including the surface and the corners farthest from the metal itself. Ion movement in water works like heat spreading through a cold room from a single fire. Stand next to the fire and you are warm in seconds. Sit in the far corner and you wait. The heat reaches you, but it takes time. Copper ions work the same way. First, clean the copper. Scrub it with a small pinch of salt and a splash of white vinegar. The acid in the vinegar strips the outer oxidation layer off the metal surface. That is the dull brown or green coating you sometimes see on old copper pipes or old pennies. That coating is still copper, but it slows how quickly ions release into the water. You want bright, clean metal underneath. After scrubbing for about 30 seconds, rinse the copper piece thoroughly in clean water. You should see a slight shine on the surface where the oxidation came off. Place the cleaned copper piece into the bottom of your container. Fill the container with your water. Room temperature water works faster than cold. Cold water slows ion movement the same way cold slows everything. A drop of milk in a hot cup of tea spreads through the whole cup in a few seconds. The same drop in a cold glass takes several minutes to move. Warm or room temperature water is not required, but it makes the process faster. Now here is the step most people skip. And it is the one that separated a Norse crew that made landfall healthy from one that spent the last weeks of a crossing too sick to manage the sails. Wait, not 1 hour, not 2. Overnight, 6 to 8 hours minimum. The water needs to sit undisturbed with the copper resting on the bottom for at least 6 full hours before you use it. Fill the container before you go to sleep. It is ready when you wake up. That is the same cycle Norse sailors would have followed. Fill at dusk, drink at dawn, copper working through the night without anyone needing to watch it. After 6 hours, lift the copper piece out. Look at it. The surface will be slightly duller than when you placed it in. Not green, not heavily corroded, just a little less bright. That is normal. That dullness means ions left the surface and entered the water. Rinse the copper piece and set it aside to dry until the next use. Now smell the water. There should be no smell at all. Bacteria in water produces a faint organic note, slightly earthy, slightly off, slightly sweet in a way that does not feel right. If that smell is absent, the copper did its work. Hold the container up to light from a window. The water should be fully clear, not hazy, not cloudy, clear through. That is the complete test. Your hand lifting the copper, your nose at the rim of the container, the light coming through the glass, no laboratory, no test strips, no equipment. Norse sailors 300 kilometers from the nearest shoreline had exactly the same tools available. What you just built operates on the same physics that kept Norse trading crews functional across 4 continents for 300 years. This channel covers dozens of techniques exactly like it, each one set aside for the same reason, because it could not be turned into a recurring charge. If that matters to you, subscribe. This is where that knowledge lives. One vessel solves one problem for one household for one day. What a Norse settlement of several hundred people did with the same principle at full scale, and what that means for a modern household that wants real independence from the supply chain, is the part that changes how you think about the cost entirely. The Trelleborg Ring Fortress, built around 980 CE and documented in precise detail by archaeologist Else Rosdahl in the Vikings, published by Penguin in 1987, housed between 400 and 500 people in a fortified settlement built for long-term occupation through harsh Scandinavian winters. Excavations at Trelleborg, with findings held at the Danish National Museum in Copenhagen, recovered copper and bronze vessels from the communal cooking and water storage areas, the same oligodynamic property, applied at garrison scale, not one family, a military community, no water treatment facility, no chemical supply, no infrastructure that required a specialist or a contract. Copper in the vessels, water in the vessels, time doing the work. At household scale, one copper fitting the size of your thumb, rinsed and reused daily, will last years without any loss of effectiveness. Decades if you keep the surface clean. The entry cost is $1. Once, no bills after that, no parts to replace, no infrastructure to maintain, no asking anyone's permission. There is one condition where this works more slowly than the numbers above suggest. Norse craftsmen understood it and accounted for it in the design of their ships and settlements. The way they solved it is the last thing in this script: cold water. Specifically, water that is very cold, below about 10 degrees Celsius, which is the temperature of water pulled straight from a cold ground well, a winter stream, or a container left in an unheated space overnight. Ion movement in water slows with temperature. At very cold temperatures, the copper releases ions more slowly, and those ions travel through the water more slowly. The same 6-hour cycle that works perfectly in a room temperature container can take 10 to 12 hours in cold water to reach the same result. Norse crews operating in northern waters understood this practically, even without naming the chemistry behind it. The Landnámabók, the Icelandic Book of Settlements, compiled around 1100 CE, records the water sources and storage practices of Norse colonists establishing permanent settlements in Iceland, one of the coldest inhabited environments in the North Atlantic. What the archaeological record of Norse longhouse interiors shows, documented by Else Rosdahl and the Vikings, is that water vessels were kept inside the longhouse, within the same heated space shared by the crew, the livestock, and the stored goods. The interior of a lived-in building warmed by bodies and fire stayed well above the temperature of the ground outside. The copper worked on its own schedule inside that warmth. The fix today is the same. Keep the container inside, away from cold concrete floors, away from unheated storage spaces, away from cold air near exterior walls. Now, let the temperature of a lived-in room do what the Norse longhouse did, or simply wait longer. 12 hours instead of 6. The copper does not stop working in cold water. It works at the pace the temperature allows. Nothing about the technique fails. It just takes longer. This is not a flaw to work around. It is a physical property of water that applies to everything, copper included.
Not a flaw.
And the Norse solution, keeping water where people live, required no modification to the technique, no additional material, and no additional cost. The Gokstad ship is in a museum in Oslo. The copper fittings that were part of it when it carried a crew across open water in 900 CE are still there, still intact. The metal did not degrade, the property did not leave. If you dissolved a fragment of that copper in a glass of water this morning, the oligodynamic effect would operate exactly as it operated for the crew who depended on it 1,000 years ago. The physics is still running. What you built this morning does the same thing. I do not know what brought you here. It does not matter. It works either way.